Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Today is our 19th lecture of Discrete Structures CSC 102. In the previous lecture we have studied relations, their properties, reflexive, symmetric and transitive relations, equivalence relations and their properties. We have also studied the properties of congruous modulo 3 and modulo n, and we have divided the set Z of integers into equivalence classes. We have also studied transitive closure of relations, combining relations and partial order relations. The partial order relation is basically the reflexive, antisymmetric and transitive relation. And at the end we have ended at Hayes diagrams. Today we are going to start functions. Functions basically are the foundation of you can say any type of mathematics, for example calculus, linear algebra, ODEs, and this is basically a basic concepts of mathematics. It comes in basic concepts of mathematics. Basically functions are special kind of relations. We'll discuss it later, what kind of relations could be functions. We shall study also the definition of function, and we shall try to understand what is a function with the help of examples. Then we shall go to one-to-one function, one-to function, and then if we have time today we'll study also the bijective and inverse functions. If not, we'll study some of these topics in the next lecture. So I repeat here some of the concepts of relations just to remind you what is the relation. By definition, as you know, any relation between two sets, basically it is the subset of the Cartesian product of two sets A cross B. As you can see in the previous lectures, if we have two sets A and B, a binary relation R from A to B is basically the subset of A cross B. In other words, a binary relation we have R, basically we denote it as ARB if such that AB belongs to R, and if AB doesn't belongs to R, we denote it like this, AR, and we draw a bar under the R, or we can denote it as AR and cross it B. So we have studied some one-to-one relations, many-to-many, one-to-many and many-to-one relations. I repeat here some of them. As you know, if we have a set A and a set B, we take the Cartesian product here of A cross B. You know how we take the Cartesian product of two sets. Now we define a relation between from A to B. If we take the first element of A, 1, we add, rule is basically what is the relation, that is we add 4 to the elements of A. So 1 plus 4 is 5, 2 plus 4 is 6, 3 plus 4 is 7, 4 plus 8, 4 plus 4 8, and 5 plus 4 9. So this is basically the relation, and the first elements of the ordered pairs of any relation is basically called the domain of that relation, and we denote it by DOM of R. R is basically the relation. The first elements basically 1, 2, 3, 4, 5. This comes in the domain of that relation, and the range is basically the second element, all the second elements in the ordered pairs of the relation. This is called the range of that relation, or we can if the range is equal to the whole set B, basically the set B is called also the codomain. We shall study also it in when we shall study the functions. So this relation R, which we have defined here, if we want to show it in a diagram, we can make a diagram to show this relation. That relation was basically 1, 4. We write the elements of the set A here like this, and the set B like this. This is basically the set A, this is basically the set B. We write the elements here of A and of B here. Now we see here what is the relation. 1 is related to 5, 2 is related to 6. So 1 is related to 5, 2 is related to 6. This diagram basically show the relation R between the elements of the sets A and B. We have studied also many-to-many relation in the previous lecture of relation. You can see we have defined this relation. In this the relation is has visited, Ahmed has visited Paris, Ahmed has visited Dubai here, Peter has visited London, New York, Cyprus, and Ali does not or has not visited any of the cities. This Javeria and Hamad has visited several cities, but note that here Ali has not visited any of the city in the set B. This is basically the set A, this is set B, and the relation is basically the subset of the Cartesian product of A and B. So note that we'll discuss this point. Ali is not in the domain. Basically Ali is in the domain, but you can say that Ali has not visited. Here Ali is not in the domain means that Ali has not visited any of the cities, but still Ali is in the set A. It is in the domain. So this is basically the many-to-many relation. Means in the first set, Ahmed, or you can say the first element of set A is related to more than one elements in the set B. Similarly, any element in the set B is related with more than one elements in the set A. So we can say it as a many-to-many relation. Next, we have defined many-to-one relation. In this set A, basically this is set A of persons and this is set B of weights. This is also a relation because and this is many-to-one relation because many elements in the first set are related with one element in the set B in the second set. So this we can say many-to-one relation. Next is one-to-many relation. Basically one element in this set A, you can say this is set B. One element in the set A is related to many elements in the set B, and this element of set A is related to many elements in the set B. Now these are relations, and we have studied four kind of relations: one-to-one, many-to-many, many-to-one, and one-to-many. Now functions basically are special types of relations which satisfy two additional conditions. Now what is a function? If we have a set A and the set B, now function is basically a special type of relation which satisfy two properties. The first is this: must use it basically in this relation, function is a relation. In this relation, every element of the first set, the set A, must be used. Every element must be connected to some other element in B. And the second thing is that each value in the set, each element in the set A can only be assigned to one element in the B. If we say the elements of A are X, for example, the elements of B are Y, elements of A are X, then all those relations which satisfy these two conditions are said to be functions. Basically, roughly speaking, a function f from a set A to a set B is a relation, is basically a relation, or we can say it rule of correspondence, that assigns each element in X. There is a stress on this, or emphasis on this phrase, you can say that assigns each element of X, each element X in the set A, means every element of the set A to exactly one element in set B. So if any relation which satisfy this condition, these two conditions, is said to be a function. For example, if we say that 1 is related to 4, 4 is related to 8, 2 is related to 2, 5 is related to 6, and 3 is related to 10. Now we investigate whether this relation, basically this is a relation, this is a subset of the Cartesian product of A and B. That is, this relation, whatever this relation is, if we say that this relation R, it is basically, it contains 1, 4, 2, 2, 3, 10, 4, 8, 5, 6. So this is basically the relation which shows the relationship between the elements of A and B. Now this relation R is basically the subset of A cross B. Now if this relation satisfy these two conditions, first and second, or you can say that here must use all x's in A, all elements in A, means every element of A must be assigned to exactly one element in B. These are two constraints or conditions, you can say, which we impose on the relations. Then any relation which satisfy these two conditions become a function. That is, all x's are assigned. We check these condition. The second, no x, basically no x has more than one y assigned. How can we check that these two conditions are not satisfied or violated? As in the previous example, or in the relation we had verified here that in many-to-many relation, Ali is not assigned to any city in the set B. So this is basically an extra element, you can say that, or this element is not assigned to any element in the set B. So this relation doesn't satisfy the first condition of a function. Now the second condition of a function is basically this, that is, every element in the set A must be assigned to exactly one element in the B, in the set B. Now here this element of set A is assigned to two elements of the set B. So this doesn't satisfy the second condition of the function. in which we say that every element of A must be assigned to a single or exactly one element in the set B. So here this relation violates the second condition of a function, and the previous relation here, this relation violates the first condition as well as the second, because here you can say that Ahmed has visited two places means one element of the function is assigned to two elements or more than one elements of the set B. So this is basically, this relation doesn't satisfy the two conditions which we impose for a relation to be a function. So once again I repeat, a function from a set A to a set B is basically a relation, and usually a relation is denoted by R, and this is basically a special type of relation. We denote it by F. So here we shall denote it by F, not R. So a function is a relation which satisfy two additional conditions. The first is this: each element of A must be assigned to some element in the set B. There must not be any extra element, you can say that, which is not assigned to any other element in B. The second condition is that every or each element of A must be or can only be assigned to exactly one element in B. So these are two conditions of the function. Now we see the formal definition of a function and some notations, some of its notations. A function f from a set x to a set y, we usually denote it by this: f from x to y, and read as f from x to y. This is basically a relation from, this is a relation from x, the domain. We usually say the first set of any relation is the domain, to y, which is called the codomain. Here in the previous example, this set is basically the domain set, you can say this, and the second set is basically called the codomain. Now the codomain that satisfy two properties. This is basic function is a special type of relation which satisfy two properties. The first is every element in X is related to some element in Y. Means that there is no element in the first set which is not related to some element in the set B. The second is no element in X is related to more than one element in Y. This is the same thing we have discussed in the previous slide. So if we are given any element X in X, there is a unique element in Y, means only one element in Y that is related to X under the relation F. If we call this element Y the elements of the second set, then we say that F sends X to Y. F is basically a rule, a relation which we define between the two sets X and Y. Then we say that F sends X to Y, or we say that F maps X to Y, and we write it as X and sign of arrow Y, and we write sometimes F here, or we usually denote it like this. The unique element to which F sends X is denoted by basically is when we say that X is as F sends X to Y, we denote it Y as F of X. So we can denote it by F of X or Y is equal to F of X. Usually you see you see functions like this, and it's called F of X, or the output of F for the input x, or the value of f at x, or the image of x under f, because this is basically, if we have x here, f basically sends 1 to the elements here in B, so we can write it as f of 1, which is basically 4. 4 to 4 we can write f of 1 means f sends 1 to 4, or f of 1 is equal to 4, we can write it as also. Or we say that this is basically the image of 1. 4 is the image of 1, here 2 is the image of 2, 10 is the image of 3, and these elements we can say them pre-image. This is basically 3 is the pre-image of 10 and 10 is the image of 3. So the set of all values of f taken together is called the range of f, or the image of x under f. Symbolically we can write it as range of f, image of x under f, or this range of any function is basically only those elements. Here the whole set B is called codomain, but the elements which are related to elements of x, if we have some other element here, for example 12 here, then the codomain contains 12, but the range contains only these elements. So the range is basically only that set, the range of f, range of or image of x under f contains only those elements of the set y which are related to x under f for some x in x. We'll study it with the help of examples also. For example, here if we have this x set and this y set, now the codomain basically here, codomain is the set y, but range is range of f basically contains only 3 elements, this one and this one, because only these 3 elements are related to elements of x. So range is basically y1, y3 and y4. This is the range. Now functions can be expressed as the arrow diagrams, as we have expressed the relations by using arrow diagrams. The same thing, using the same concept, we can use functions, we can express functions as arrow diagrams. So this arrow diagram does define a function, because now this is a function or not, we must check 2 additional properties. Every element of x has an arrow coming out of it. Means how to check whether this arrow diagram is a function or not? We have to check 2 properties, the same properties which we impose in the definition of function. There is an arrow coming out of every element in the x. So this is the first property, means every element of x has been utilized or related to some element of y. Now the second condition is no element of x has 2 arrows coming out of it that point to 2 different elements of y. Means we have from each element there is only 1 arrow coming out. If there would be some here, x is related to y3 and x is related to y1 also, then this is not a function, because there is an element x1 in x which is related to 2 different elements in y. This violates the second condition of the function. Here means the two. No element in X is related to more than one element in Y. But if we have this case, X1 is related to this one also, then X1 is related to Y1, X1 is related to Y3, means X is related to two different values of Y, then this is not a function. So this is how we can express functions by using arrow diagrams. Now we see here some of the examples, and we shall investigate whether the given arrow diagrams express functions or not. Which of the following diagrams define functions from X is given to Y is given. Now the first we check, this is a relation. Obviously this is a relation, but now we have to check whether it is a function or not. So we have to check two properties. The first is each element of the set X must be utilized, means there must be an arrow coming out of each element of X. So arrow coming out of A, arrow doesn't coming out of B. So this violates the first condition of the function, because there is no arrow, or B is not related to some element in Y. So this is not a function, not function. This one is. Now this one we check the first condition, each element of X is assigned to or related to some element in Y. So this is true. First condition is true. Now the second condition we check, each element of X must be related to exactly one element of Y. Now here A is related to only one element in Y, B is related to only one element, but C is related to two different elements of Y. This C is related to 2, C is related to 3. So this is not a function also, because it violates the second property of function. So this is also not function. Now we check here. The first condition is basically each element of X is related to some element of Y. So here we can see that A is related to some element in Y, B is related to some element in Y, C is related to some element in Y. So first condition is true. Now the second condition we check here, each element in X of X must be related to exactly one element in Y. A is related to only one element, B is related to only one element, C is related to only one element. So this is a function, because this is a relation which satisfies the two additional condition which we impose that relation to be function. So this diagram satisfy the additional two properties, therefore this is basically a function. This arrow diagram you can say expresses or shows a function. Here one thing is to be noted, that here C is related to two different elements. This is not allowed by the second condition of function, but two elements here may be assigned to one element in B, in the set Y, sorry. Here A is related to 3, C is related to 3. A is related to exactly one element, C is related to exactly one element, but that element is same. 3 is related to A, C is related to 3, A is related to 3. So it can happen. So there is no problem for such type of situations, that more than one element of X can be related to one element of Y, but one element of X cannot be related to more than one element of Y. So this situation is not allowed, this situation is allowed. I repeat here that any element of X cannot be related to more than one element of Y. Just you can see in this example. But more than one element of X they can be related to one element of y. This is allowed, but this is not allowed. So I hope you understand how we can see that whether a relation satisfy the two conditions which we impose for that relation to be a function satisfy or not. Now we move to the inverse image of a function. What is the inverse image? Basically, the elements of y here, these are images of the elements of x under the relation f. For example, f. So x is this, y is the set here. The elements, this is basically the image of a, 2 is image of b. You can see here 1 is image of b, 3 is image of a, and 3 is image of c. Now we define the inverse image. If we are given an element y of the set y, for example this is set x, this is set y, this is x, this is y. If we have any element y in y, there may exist elements in x with y as their image, as here b is basically, b is the image of 1, b is the image of 4, a is the image of 2. Now if f of x is equal to y, then x is called pre-image, then the elements of x which are related to some element of y, they are basically called pre-image of y or an inverse image of y. Means if we denote f of 1, what is f of 1 here? This is basically b. And if we say that this b is basically image of 1 and 1 is pre-image of b or inverse image of b, and we write it as b is equal to f inverse of 1. Sorry, 1 is sorry. Here the set of all inverse images of y is called the inverse image of y. Symbolically we write it as the inverse image of y is basically all those elements of x such that f of x is equal to y. Means inverse image here in this example is what? Inverse image of, for example, if we write the b, inverse image of b is the inverse image of b in this example is what? It's basically image has 1 and 4, because f of 1 is b and f of 4 is b. So this is basically called the pre-image of b or the inverse image of b, and the set of all inverse images of y, because one element in the set y can have more than one pre-images or inverses. As you can see here in this example, let x and y be two sets 1 2 3 4 a b c d e, and define f from x to y by the following arrow diagram. Now let a is 4, c is this, d is this. Find f of a. We have to find the image of a. We have to find f of x. We have to find the image of x. We have to define f inverse of c, means pre-image of c, and pre-image of d or inverse image of d, capital D. Now as here you can see that a is 1 4, and what are the images of 1 and 4? Image of 1 is b, image of 4 is b. So you can say here image of a A is basically 1 4, and this contains only what? B. So image of A is B, and image of what is the second? C. Now we have to find the image of X. This is the whole set X. Now image of X is basically what? This all those elements in Y which are related to some element in X basically is called the image. So this element is related to element in X, this element is related to some element in X, this element is not related, this element is related, this element is not related. So only those elements will come in the image of X which are related to some elements in the set X. So A, B and D is basically the image of, you can say, X. We can write it as also, see, this is A, B and D. So this is the set of the image set of X. Now we write the inverse image of C. C is basically AB. Now we have to the inverse image of, we can write it as inverse image of D, or we can write it as F is basically the inverse, F inverse of D. This is D, no, C, the inverse image of C. After that we shall write also the inverse image of D. Now we have to write the inverse F inverse C means inverse image of C. The inverse image of C inverse, F inverse C. Now C contains what elements? Basically C contains A, B. Now we see here in the arrow diagram what is the inverse image of A. This is 2, and what is inverse image of B? This is 1 and 4. So the inverse image of C is basically 1, 2 and 4. Similarly, we can write the inverse image of D. D is what? CE. F inverse of D, this is what? D is basically CE, but C and E are not related to any element of X, means they are not images of any element of X, therefore they don't have pre-image or they don't have inverse image. The elements in Y, those elements in Y which have pre-image or which are related to some element of X, only those elements can have inverse images, because they are not images of some elements of X. You can say like this also. So inverse image of D is the empty set, or you can say that phi, the empty set. There is no element in the inverse image of D, because elements in the D are not related to some elements of X. We take another example, how to find the images, inverse images, range, or whatever the basic calculation which are involved in the functions. Let x is equal to abc, y is equal to 1 2 3 4. We have two sets and function is defined here by the arrow diagram. Define a function from x to y by the arrow diagram in this figure which is given here. So we have to write the domain and codomain of the function. Now what is the domain of this function? We can write it as we can write it easily. Domain is this function f is basically a, b, c, or you can say this is x, and the codomain is codomain of f is the second set which is y, the complete set. And if we want to write the range of this function, then the range of this function is basically, it contains only those elements of y which are related to some element in x. So these are 2 and 4. The range of f is 2, 4, because 2 is related, 4 is related to some element in x. 1 and 3, they are not related to some other element in x. So therefore they don't come in the range of this function. So find f of a, f of b, and f of c. What is f of a? You can write it easily by looking at the arrow diagram. F of a is 2, f of b is 4, f of b is 4, and f of c is again 2. This is f of c is again 2. F of c is again 2. Now what is the range of the function? The c part of this exercise or example, range we have already written. Now is c is an, now the d part is c an inverse image of 2? Is b an inverse image of 3? No. Now here we have 2, c is related to 2, 2 is the image of c, and inverse image of 2 is c. We can see here c is related to 2 here, so inverse image of 2 is, yes, this is true. Now is b is the inverse image of 3? The b is the inverse image of 4, not 3, so this is basically false. Find the inverse image of 2, 4 and 1. The inverse image of 2 is basically the inverse image of 2. First we define the inverse image of 2, basically f inverse of, you can write 2. F inverse of 2 is basically is a set which contains the inverse images of 2. 2 is, the inverse image of 2 is a, inverse image of 2 is c. So this contains two elements, a and c. Now inverse image of 4 is b. F inverse of 4 is what? B. This is a you can see singleton set. Inverse image of 1, inverse image of 1 is nothing, because inverse image of 1 is you can say phi or empty set. Now last part is represent f as a set of ordered pairs. So next we shall, then f can be represented as a set of ordered pairs. How we can represent it? F is basically, it is a relation basically which satisfy two additional properties. Now f, in f, a is related to 2, so there must be an ordered pair a 2. B is related to 4, so b will come here with 4, b 4. Again c is related to 2, so here we can write here c is related to 2. So these are only ordered pairs which will come in the set of ordered pairs of this function, because no other element is related to some element in x. So this is basically the relation which is also a function, but remember that this is the subset of Cartesian product of x and y. X and y. So this is basically the we can write any function in the form of or in the set of ordered pairs. I hope you understand the basic calculations involved in functions. What is image, what is pre-image, or what is inverse, what is range, what is codomain, what is domain, and how we can represent a function or a relation. This is a relation which satisfies two additional properties. How we can represent function in the form of in this form of the set of ordered pairs. Now we move to some typical or classical examples of the functions. The identity function on a set. Given a set X, define a function IX. Usually people denote it by I, or they write it IX. The IX is basically the domain set, or you can simply denote it by small letter. Some people define it by small I of X, like this, or many other notations are there for the identity function, but the most common which we use is this or this. Given a set X, define a function IX from X to X. Identity function is always defined on a single set, basically from the set X to the same set X. And how we define it? I of X, Ix of X is equal to X. This is basically the capital X, and these are the small x. These are basically the elements of X. So the function Ix is called, this function is called identity function, and it sends each element of X to the element that is identical to it, or you can say that it sends each element of X to the same element of X. Means the identity function can be pictured as a machine that sends each piece of input directly to the output without changing it anyway. Means you can say if we have a function 1 2 3, and here we have 1 2 3, this is X, this is X, and we define an identity function I capital X, and we define a function Ix from X to X. Now what will be the arrow diagram of this identity function? If we apply Ix on 1, it will remain 1 2 2 3 3. So means the elements in the identity function doesn't change. Ix of 1 is 1, Ix of 1 is 1, Ix of 2 is 2, and Ix of 3 is 3. This function doesn't change the element remains same. So this is basically the identity function on a set. Now we take another example of the function. A function defined on a power set. Because in sets we have discussed what is the power set. P of A denotes the set of all subsets of the set A, and we define the function f from power set of A. Is A, we take ABC. The set A is taken to be A, B, C. So the power set of this set A basically contains 2 power 3, which is 8 elements. As we have discussed, the number of elements in the power set is basically 2 power 3. 3 is the number of elements in this set A. So this is 8, so it contains 8 elements, 1 2 3 4 5 6 7 8. How we define function on this set to the set Z power non-negative? Means here Z non-negative means this is basically the set of integers which contains only non-negative integers, not the negative. In non-negative integers we have 0 1 2 3 4 so on. But if we here we say that Z positive, then this set doesn't contain 0. This set doesn't contain 0. It starts with 1, contains 1 2, it contains 1 2 3. So this is the difference between Z non-negative integers and Z positive integers. So how we define the function f of x is basically the number of elements in X. X is basically any subset of A, means X is in the power set of A. So this function is defined like this. This is function f. Now the first set is basically, it contains 0 elements, so it maps onto 0. The second set contains 1 element, it maps onto 1, third element onto 1, fourth element onto 1, because these sets contains 1 element. Here these three sets are basically mapped onto 2, because these three sets contain 2 elements, and at the end last element of this power set is mapped onto 3, because it contains 3 elements. So such type of function we can define on the power set of any set. Another function or example of the function, a Boolean function. This is basically a 3-place Boolean function defined from the set of all 3 tuples of 0s and 1s to the set 0, 1. And we define this function as follows. For each triple x1, x2, x3 of 0s and 1s, f of x1, x2, x3 is equal to x1 plus x2 plus x3 mod 2. So how we can define, or how we can perform the calculations in this function? If we have f of 1, 1, 1, means x1 is 1, x2 is 2, x2 is 1, x3 is 1, then 1 plus 1 plus 1 is basically 3 mod 2, and we can calculate 3 mod 2 is 1. When 3 is divided by 2, the remainder is 1. Similarly, if we have f of 1, 1, 0, so we have 1 plus 1 plus 1 plus 0 is basically 2, 2 mod 2. When 2 is divided by 2, the remainder is 0. So this is again a function. The input of this function is basically, we can draw, write a table, and this is basically input output table, which we have studied in logic. The inputs are x1, x2, x3. You can take them as propositions, and these are basically the truth values of these 3 propositions. The output is basically defined by using this Boolean function, which is x1 plus x2 plus x3 mod 2. If we give the input this 1, 1, 1 to the function, we have 1 plus 1 plus 1, this is 3 mod 2, 1. If either of 2, x1, x2 or x3 are 1, then we have 0. If either of x1, x2, x3, basically if 2 of them are 0, for example 0, 0, 1, then we write here 0 plus 1 mod 2. So this is basically 1 mod 2, and you know that when 1 is divided by 2, the remainder is 1, because 2 doesn't divide 1, so 1 will come as it is. So we can write the outputs like this, as we have written here. As we have calculated here, we can calculate the outputs for all possible inputs. For first we have 1, for second we have 0, 0, 0, 1, 0, 1, 1 and 0. So this is basically an example of Boolean function. Now, how to check whether a function is well defined or not? That is, that relation satisfy the additional true properties or not. A very famous example in the calculus, you have seen it before, I hope. Sometimes it happens that a function is not really well defined, and you think that it is a function, but in actually it doesn't satisfy the 2 additional properties which we impose on the relation to be a function. For example, if f of x is a real number y such that x square plus y square is equal to 1. Now this is only a relation but not the function, because if we check the two properties which we impose on the function, this relation doesn't satisfy. Here the first, there is no y which satisfy the given equation, or you can say there are two different values of y that satisfy the equation. For instance, if x is 2, then there is no real number such that x square plus y square is equal to 1. And when x is 0, both -1 and 1 satisfy the equation this. So for any one value of x, we have two values of y, which is not allowed, and this fact satisfy basically this situation doesn't satisfy the second condition of the function, because for one value of x we must have exactly one value of y, and here we have for one value of x 0 we have two different values of y which are -1 and 1. Therefore it doesn't satisfy the second condition of the function. Similarly, so this function is not well defined. Similarly, we take another example of a function that is basically I cannot say it a function because it is not well defined. It is not a function. It can only be a relation but not a function. How? If we have a set of rational numbers, we have discussed in the set theory, the set of integers, we define a function from q to z by f of m by n is equal to m, where the first element is basically the element of q, set of rational number, and the second element is of the set of z integers. For all integers m and n, with m is different from 0. Now we have to check whether this function is well defined or not, that is, this is a function or not. So we have to check the two conditions which we impose on the relation in the function. The first is that every element of the first set must be utilized, must be used. That is, every element of q here must be related to some element of z. The second condition is that each element of q must be assigned or related to exactly one element of the second set, which is z here. Now the first element, you can say that it is related to every element, any element of z, but here you can check that the second condition, that if we take two elements here which are equivalent, 1 by 2 is equal to 3 by 6, both are rational numbers. 1 by 2 we can write it as 3 by 6 because 3 1s are 3 2s are 6, so we again get 1 by 2. Now the image of 1 by 2 under this function, 1 by 2 will be 1, and image of 3 by 6 will be what? 3. Means that here 1 is not equal to 3, but here f of 1 is not equal to f of 3 by 6. But we have seen here that 1 by 2 is equal to 3 by 6. What does it mean? It means that one element of the first set is related to two different elements of the second set. So here the second condition of the function is being violated. So therefore this is not a well-defined function. It doesn't satisfy both properties of the function. So we can say that this is not a function. So this is how the functions are not well defined. There may be some error in the conditions in which you have defined on that function. So for a function, whenever you define a function, you must check the two conditions of the functions, that each every element of X must be related to some element in the second set, and the second is each element of X must be assigned to exactly one element in Y. So here I think it's enough for today, and we stop it here. In the next lecture we shall continue some other properties and definitions related to functions, which are one-to-one function, on-to function, bijective function, which is also the one-to-one correspondence, and we shall discuss also inverse functions and some other concepts, basic concepts related to the functions. Until the next lecture, Allah Hafiz.